This video is brought to you by Altium Designer. Welcome to my STM32 CubeIDE course specifically designed for beginners. In this course, we will take a step-by-step approach to ensure that you gain a solid understanding of how to use CubeIDE for programming the STM32 microcontroller. Throughout this course, I will be using the most popular STM32f103c8t6 microcontroller board, which is also known as Bluebell, and for uploading the program, I will use the ST-Link V2. Since this course is for the absolute beginners, so I will try my level best to explain each and every detail, including number 1, STM32 Bluebell board technical specifications and pinout. Number 2, what is CubeIDE? And number 3, how to download and install STM32 CubeIDE. After covering the most basic things, then I will practically show you how to use the most commonly used electronics components with the STM32. Since this course is for the beginners, so first I will start with the easiest example, which is controlling the STM32 onboard LED. Then in the second example, I will show you how to connect and control external LEDs. These LED blinking examples will help you in understanding how to turn on and turn off any GPIO pins on the STM32. In third example, I will show you how to read a digital input on any GPIO pin of the STM32. For this, I will use a push button. We will be reading and controlling both at the same time. The STM32 board will sense the button click and then accordingly will turn on or turn off the LED. In fourth example, I will show you how to interface an I2C supported 16:2 LCD. This is one of the most commonly used LCDs. We will simply print the Hello World text message on the LCD module. In the fifth example, I will show you how to use an analog sensor with the STM32 and display its value on the I2C supported 16:2 LCD. For demonstration purposes, I will be using a potentiometer as the analog sensor. After understanding this example, then you would be able to use all types of analog sensors, like for example LDRs, flex sensors, force sensors, etc. There is a long list of the analog sensors. In the sixth example, I will show you how to connect an I2C supported OLED display module with the STM32. I will write a very basic program to print some text on the OLED display module. This is really an important example because in most of the projects you will need an OLED display module to print text messages and sensor values. In seventh example, I will explain how to make a simple distance measurement system using the most popular HC-SR04 ultrasonic sensor. We will simply measure the distance and then print it on the I2C supported SSD1306 OLED display module. These examples will help you in getting started with the STM32 and CubeIDE. So without any further delay, let's get started. Throughout this course, I will use the STM32 Bluebell board, which is based on the STM32 F103c8t6 microcontroller unit from ST Microelectronics STM32F1 series. The STM32 Bluebell controller board is based on the ARM Cortex M3 and is commonly known as the Bluebell development board. Let me share with you some of its key information. It is based on the ARM Cortex M3 32-bit RISC processor, which offers a good balance between performance and power efficiency. The STM32 F103C8T6 microcontroller typically operates at a maximum clock speed of 72 MHz. It comes with different variants offering various amounts of flash memory. The most common one is 64 KB of flash memory, which is used to store the program code. It has 20 KB of SRAM, static random access memory, that is used for data storage during program execution. The MCU includes a wide range of peripherals including GPIO, general purpose input-output ports, timers, USART, SPI, I2C, ADC, analog to digital converter, and more. The operating voltage typically ranges from 2.0 volts to 3.6 volts, making it suitable for low power applications. To program and develop applications for the STM32 F103C8T6 MCU, you can use the STM32 CubeIDE, which is an integrated development environment provided by ST Microelectronics. Additionally, you can use various other development tools and programming languages like C or C++ and assembly. The STM32F1 series has been widely used in various applications including industrial automation, consumer electronics, IoT devices, robotics, and more. Its versatility, performance, and affordability make it a popular choice among developers and hobbyists for various embedded projects. It has a total of 40 pins, 20 pins on each side. It has two 3.3 volt pins connected to the onboard 3.3 volt regulated power supply, which is used to power up the onboard components including the microcontroller and other external components like sensors and breakout boards. So if you need 3.3 volts to power up your sensors, you can simply connect 3.3 volt from any of these two pins. It has three ground pins, one on this side and the other two on this side. All these ground pins are interconnected, so you can take a ground connection from any of these three pins. This 5 volt pin is the input power pin, means you can connect an external regulated 5 volt power supply to this pin to power up the STM32 board. You don't need to worry about the microcontroller. The onboard 3.3 volt regulator will convert the 5 volts into 3.3 volts. While performing your initial experiments, you don't need to connect an external 5 volt regulated power supply. You can just use your laptop as the power source. But sooner or later you will need an external power supply because it's impractical to use your laptop or PC as the power source. So I recommend you should build yourself this 5 volt and 3 amps power supply. I have a detailed video on its designing and making, and later in this video I will use this 5 volt power supply to power up the STM32 controller board. It has a total of 32 GPIO pins numbered as B0 to B15, C13 to C15, and A0 to A15, while in the pinout diagram these are numbered as PB, PC, and PA. It has a total of 10 analog pins starting from A0 to B1. These pins are connected to the built-in analog to digital converter ADC of the microcontroller and can be used to measure analog signals. It has two I2C supported ports. The I2C one is available on pins B6 and B7. B6 is the SCL and B7 is the SDA. The I2C second port is available on pins B10 and B11. B10 is the SCL and B11 is the SDA. It has three serial ports. The USART one is available on pins A9 and A10. A9 is the TX and A10 is the RX. USART2 is available on pins A2 and A3. A2 is the TX and A3 is the RX. USART3 is available on pins B10 and B11. B10 is the TX and B11 is the RX. And it also has pins for the SPI, PWM, and CAN. All these pins are clearly labeled. Let me also tell you, when you hold the STM32 controller board like this, all the pins on this side from B9 to B12 are 5 volt tolerant except the B5 pin. PB-5 or B5 is 3.3 volt standard pin. All the pins on this side from V battery to the reset pin are 3.3 volt standard pins except the B10 and B11, which are 5 volt tolerant pins. These 4 pins on the STM32 board are the SWD serial wire debug pins that allow you to connect a debugger or a programmer like the ST-Link V2. The ST-Link V2 allows you to program the firmware onto STM32 microcontrollers and also provides debugging capabilities. It connects to the STM32 microcontrollers SWD pins for programming and debugging operations. It is designed to work seamlessly with the STM32 CubeIDE, which is an integrated development environment provided by ST Microelectronics. I think I have shared enough valuable information with you guys, and now it's time to download and install the STM32 CubeIDE. Search for the STM32 CubeIDE. Click on this link. While you are on the STM32 CubeIDE official page, go to the STM32 developer zone and from the drop down list select STM32 CubeIDE. Click on the download STM32 CubeIDE button. Select Windows. Accept the license agreement. Click on the register button. Click on the create account. Enter the required details. Finally, check the box and click on the register button. Next, open your email account and click on the validate now. Complete your registration by entering your password. Click the submit button and you will be notified The registration has been completed. Please log in here. Enter your registered email ID and password and click on the login button. Now you can click on the download STM32 CubeIDE. Click on the Windows, accept the license agreement, and start downloading the STM32 CubeIDE. Extract the downloaded zip folder. Open the folder and run the exe file to start the installation process. The STM32 CubeIDE has been installed. You will see the STM32 CubeIDE shortcut on the desktop. In this first example, we are going to control the STM32 onboard LED, which is connected to PC13 pin. Before we start the programming, first we will need to connect the STM32 board to the laptop or PC. For this, we are going to use the ST-Link V2. Simply connect the ST-Link V2 3.3 volt and ground pins to the 3.3 volt and ground pins on the STM32 board. Connect the SWCLK and SWDIO pins of the ST-Link to the STM32 SWCLK and SWDIO pins. Finally, connect the ST-Link V2 to your laptop or PC. Open the STM32 CubeIDE software. Select a directory as workplace where you want to store all your projects, or you can go with the default address. Finally, click on the launch button. STM32 CubeIDE will display the welcome screen indicating that the IDE has been successfully launched. To start a new project, go to the File menu, then to New, and click on the STM32 project. STM32 CubeIDE may take a moment to load and download the necessary libraries. Please be patient during this process as it may take some time depending on the speed of your internet connection. On the target selection window, and while the MCU selector tab is active, select the commercial part number, that is STM32f103c8t6. Select it from the MCU's list and then click on the next button. Write the project name. Select the targeted language, target binary type, and targeted project type. On the Pinout and Configuration tab, click on the System Core and select Sys. Click on the Debug and select Serial Wire. Click on PC13 and select GPIO_output as the onboard LED is connected to this pin. Finally, click on the Save button. If it asks you, do you want to generate code, click Yes. Again, press the Yes button. STM32 CubeIDE will generate the necessary code based on your pin configuration and open the associated perspective. This perspective provides you with the appropriate tools and views for further development and customization of your project. Scroll down. Now in while function, we will write code for blinking the LED. Once the code is completed, click on the hammer icon or build. There are no errors and warnings. Now we can click on the play button. Click on the debugger tab. Select ST-Link. Click on Show Generate Options. Set the reset mode to Software System Reset and click the Apply button, and then click the OK button. You can see the onboard LED is blinking. We just built our first LED blinking project. In this next example, I'm going to explain how to control external LEDs. Altium Designer is the world's most trusted PCB design system. Altium Designer enables engineers to effortlessly connect with every facet of the electronics design process. Over 35 years of innovation and development focused on a truly unified design environment makes it the most widely used PCB design solution. With Altium Designer, you can create PCB designs with an intuitive and powerful interface that connects you to every aspect of the electronics design process. Route it your way through any angle, tune for the delay, push, slide, and walk around faster than ever. Easily work together with your mechanical team and forget about the days of swapping design files. Every design change stays in sync between Altium Designer and SolidWorks PTC Crew, Autodesk Inventor, Autodesk Fusion 360 or Siemens NX. Interact and collaborate with mechanical designers like never before in a photorealistic 3D design environment. One of the best things about Altium Designer is that you can share your designs with your team members using Altium 365. They can check your design, leave comments, and if there are any issues, they can fix them from anywhere in the world. Altium Designer also uses the world's fastest component search engine, Octopart, so you won't have any difficulty in searching for components. Links to the Altium Designer, Altium 365 and Octopart are given in the description. In the second example, we are going to control external LEDs, but to keep things simple and easy to follow, first let's start with a single LED and afterwards we'll control multiple LEDs. Anyway, let me explain the connections. The cathode legs of all the LEDs are connected together and then connected to the ground pin on the STM32 board. The anode legs of all the LEDs are connected to the GPIO pins PB6, PB7, PB8 and PB9 through these current limiting resistors. You can follow this circuit diagram. Before we start the programming, first we will need to connect the STM32 board to the laptop or PC. While the STM32 CubeIDE is open, go to the File menu, then to New and click on the STM32 project. On the target selection window and while the MCU selector tab is active, select the commercial part number, that is STM32f103c8t6. Select it from the MCU's list and then click on the next button. Write the project name. Select the targeted language, target binary type and targeted project type. On the Pinout and Configuration tab, click on the System Core and select Sys. Click on the Debug and select Serial Wire. Click on PB9 and select GPIO output as the external LEDs connected to this pin. Repeat the same steps for the other three GPIO pins to which the external LEDs are connected. Finally, click on the Save button. If it asks you, do you want to generate code? Click Yes. Again, press the Yes button. Scroll down. Now, in while function, we will write code for blinking one LED that is connected to B9 or PB9. Once the code is completed, click on the hammer icon or build. There are no errors and warnings. Now we can click on the play button. Click on the debugger tab. Select ST-Link. Click on Show Generate Options. Set the reset mode to software system reset and click the Apply button and then click the OK button. You can see out of these 4 LEDs, only one LED is blinking. If you replace this LED with a relay, then you would be able to control high voltage AC and DC loads. Anyway, now let's control all these 4 LEDs. I've already written some code, so I'm going to copy and paste it in the existing code. You can see I'm using the same pins B9, B8, B7 and B6. The code is exactly the same, only this time I'm controlling multiple LEDs. You can turn on and turn off LEDs and certain patterns to make some cool animations. Let's click on the play button. You can see this time I'm able to control multiple LEDs. Now you can modify this program to control less or more LEDs. In next example, I'm going to explain how to read digital input. In this third example, we are going to learn how to read a digital input on any GPIO pin of the STM32 microcontroller board. We'll be monitoring and controlling both at the same time. Each time the button is pressed, the LED is going to change its state. Anyway, let's take a look at the wiring. The anode leg of the LED is connected to the STM32 GPIO pin PA1 through a 330 ohm current limiting resistor, and the cathode leg of the LED is connected to the ground. One side of the push button is connected to the ground and the other side of the push button is connected to 3.3 volt through a 10 kilo ohm pull-up resistor. A wire from the middle is connected to the STM32 GPIO pin PB1. When the button is open, the PB1 pin reads 3.3 volt, and when the button is pressed, it reads 0 volt. You can follow this circuit diagram. Before we start the programming, first we will need to connect the STM32 board to the laptop or PC. While the STM32 CubeIDE is open, go to the File menu, then to New, and click on the STM32 project. On the target selection window, and while the MCU selector tab is active, select the commercial part number, that is STM32f103c8t6. Select it from the MCU's list and then click on the next button. Write the project name. Select the targeted language, target binary type, and targeted project type. On the Pinout and Configuration tab, click on the System Core and select SYS. Click on the Debug and select Serial Wire. Click on PA1 and select GPIO Output. Click on PB1 and select GPIO Input. Finally, click on the Save button. If it asks you, do you want to generate code? Click Yes. Again, press the Yes button. I have already written some code, so I'm going to copy and paste it in the main.c file. You can download this code from our website electronicclinic.com. Once the code is completed, click on the hammer icon or build. There are no errors and warnings. Now we can click on the play button. Click on the debugger tab. Select ST-Link. Click on Show Generate Options. Set the reset mode to software system reset and click the Apply button, and then click the OK button. You can see each time I press the button, the LED changes its state. You can replace this push button with a digital IR sensor and the LED with a relay to make a contactless AC or DC load control system. You can use any type of digital sensor. Even you can convert this simple project into a security system using a digital PIR sensor. Anyway, in next example, we are going to use I2C supported 16x2 LCD with the STM32. If you have been using Altium Designer for creating schematics and designing your PCBs and you don't know about Altium 365, then let me tell you about it. Altium 365 lets you store projects in the cloud with all the documents and components you might need to complete all your tasks. To unlock all of the functionality of Altium 365, you must first connect to your workspace, a separate environment where all your data exists. After logging into your account, you can access all of the features of the Altium 365 platform. Let me show you how to create a workspace. Click on the Not Signed In drop-down button and click on the Sign In. Click on the Register an Account. It's just a two-step process. Enter your email ID, or you can also register with Gmail and Facebook. Once you complete the registration, then come back to Altium Designer, enter your email ID and password, check the Sign In automatically box and click on the Sign In button. And your Altium 365 workspace will activate. Click on Manage if you want to change your password, your information, and you can also write about your experience in projects. And finally, you can click on the Save button. I will share more tips and tricks with you in my upcoming videos. I have added links to the Altium Designer, Altium 365 and Octopart, the world's fastest component search engine. In this fourth example, I am going to show you how to print text on this I2C supported 16:2 LCD. This is one of the most commonly used LCDs used for displaying text messages and sensor values. Let me explain the connections. Connect the VCC and ground pins of the I2C supported 16:2 LCD to the STM32 board 5V and ground pins. Connect the SCL and SDA pins of the 16:2 LCD to the STM32 GPIO pins PB10 and PB11. You can follow this circuit diagram. Before we start the programming, first we will need to connect the STM32 board to the laptop or PC. For this, we are going to use the ST-Link V2. Simply connect the ST-Link V2 3.3V and ground pins to the 3.3V and ground pins on the STM32 board. Connect the SWCLK and SWDIO pins of the ST-Link to the STM32 SWCLK and SWDIO pins. Finally, connect the ST-Link V2 to your laptop or PC. While the STM32 CubeIDE is open, go to the File menu, then to New, and click on the STM32 project. STM32 CubeIDE may take a moment to load and download the necessary libraries. Please be patient during this process, as it may take some time depending on the speed of your internet connection. On the target selection window, and while the MCU selector tab is active, select the commercial part number, that is STM32f103c8t6. Select it from the MCU's list and then click on the Next button. Write the project name. Select the targeted language, target binary type, and targeted project type. On the Pinout and Configuration tab, click on the System Core and select SYS. Click on the Debug and select Serial Via. Click on the Connectivity and select I2C2. You can see the PB10 and PB11 pins are selected. On the left side, click on Core, then INC. Right-click and select New File. Write the file name liquidcrystal.h. You can see the liquidcrystal.h header file has been added. Now copy and paste this code. Save this file. Then go to the SRC folder and create a new file. Write the file name liquidcrystal_I2C.c. Copy this code and paste it in the liquidcrystal_I2C.c file, and also save this file. You can download these codes from our website electronicclinic.com. Now go to the main.c file and add the header file. Then scroll down, and under the user code begin to copy and paste this code. The purpose of this code is to initialize and clear the LCD. On the first row we print hello and next to it we print world. Once the code is completed, click on the hammer icon or build. There are no errors and warnings. Now we can click on the play button. Click on the debugger tab. Select ST-Link. Click on show generate options. Set the reset mode to software system reset and click the apply button and then click the OK button. You can see the message hello world printed on the I2C supported 16:2 LCD. In next example, we are going to interface an analog sensor with the STM32 board and we will print its value on the 16:2 LCD. In this fifth example, I'm going to use an analog sensor with the STM32 board. I will read its value and then print its value on the I2C supported 16:2 LCD. You can see I'm using a potentiometer as the analog sensor. For this experiment, you can use any analog sensor like for example an LED or etc. Anyway, I'm going to continue with this potentiometer. Let me explain the interfacing. The 16:2 LCD wiring remains exactly the same as explained in the previous example. The potentiometer leftmost and rightmost legs are connected to the STM32 3.3 volt and ground pins, and the middle leg of the potentiometer is connected to the PB1. All the analog pins are 3.3 volt standard pins, so make sure the voltage on the analog pins does not exceed 3.3 volts. Anyways, you can follow this circuit diagram. Before we start the programming, first we will need to connect the STM32 board to the laptop or PC. I'm going to modify the previous project. Go to the I2C LCD.ioc. Click on the analog and select ADC1. And under the ADC1 mode and configuration, select IN9, which is the GPIO PB1 pin on the STM32. Click on continuous conversion and enable it. Finally, click on the save button. If it asks you, do you want to generate code? Click yes. Again, press the yes button. I have already written this code. Simply copy and paste this code in the main.c file. You can download this code from our website electronicclinic.com. Once the code is completed, click on the hammer icon or build. There are no errors and warnings. Now we can click on the play button. You can see the value changes as I rotate the knob of the potentiometer. You can use this same program with all types of analog sensors for reading and displaying the raw data. Next, I'm going to explain how to use an I2C supported OLED display module with the STM32 controller board. In this sixth example, I'm going to show you how to print text on this I2C supported STM32 OLED display module. In most of your upcoming projects, you will need this OLED display module for printing text messages and sensors values. In this example, I will print the hello world message on this OLED display module. Anyway, let's take a look at the connections. The STM32 OLED display module VCC and ground pins are connected to the STM32 3.3 volt and ground pins. The SCL and SDA pins are connected to the STM32 GPIO pins PB10 and PB11. PB10 is the SCL and PB11 is the SDA. You can follow this circuit diagram. Before we start the programming, first we will need to connect the STM32 board to the laptop or PC. While the STM32 CubeIDE is open, go to the File menu, then to New and click on the STM32 project. STM32 CubeIDE may take a moment to load and download the necessary libraries. Please be patient during this process as it may take some time depending on the speed of your internet connection. On the target selection window and while the MCU selector tab is active, select the commercial part number, that is STM32f103c8t6. Select it from the MCU's list and then click on the next button. Write the project name. Select the targeted language, target binary type, and targeted project type. On the Pinout and Configuration tab, click on the System Core and select SYS. Click on the Debug and select Serial Via. Click on the Connectivity and select I2C. You can see the PB10 and PB11 pins are selected. Click on the I2C Speed mode and select Fast mode. Finally, click on the Save button. If it asks you, do you want to generate code? Click Yes. Again, press the Yes button. Next, we will add these .c and .h files exactly the same way as we did in the example number 4. We will add .c files in the src folder and .h files in the inc folder. You can download these codes from the article available on electronicclinic.com. You can see all the required .h and .c files have been added. Now we can close all these files because these are already added in the src and inc folders. I have already written the program, so I'm going to copy and paste it in the main.c file. For the step-by-step explanation, read my article. I started off by adding the required header files. The purpose of this section of code is to print the Hello World message on the OLED display module. You can see the Hello World message on the STM32 OLED display module. Now you can add this OLED display module in all those projects where you need to print text or sensor values. In the next example, we are going to measure the distance using the ultrasonic sensor, and then we will print the measured distance on this OLED display module. Get your Altium 365 workspace activated because Altium 365 provides a useful solution in cases when you are facing difficulties with your PCB design and unsure of your next step. You can share your project in Altium Designer or on the web with any user in just a few clicks. You will have full control over who you want to give read-only access for, let's say, comments and design inspections. and who you want to give read-write access to allow full global collaboration by a geographically dispersed team with editing performed through Altium Designer. Let me show you how to share your project. Simply right-click on the project name and select Share. Write the user's email. Select Read or Write Permissions from the drop-down menu on the right and click on the Share button. It's just that simple. I've added links to the Altium Designer, Altium 365 and Octopart, the world's fastest component search engine. In this 7th example, we are going to make a distance measurement system using the HC-SR04 ultrasonic sensor with the STM32 microcontroller board. We'll measure the distance in centimeters and then we'll print it on the STM32 OLED display module. Anyway, let's go ahead and take a look at the connections. The OLED display module wiring with the STM32 remains exactly the same. The ultrasonic sensor, VCC and ground pins are connected to the STM32 board, 5-volt and ground pins. The echo and trigger pins are connected to the STM32 GPIO pins PB8 and PB9. PB8 and PB9 are 5-volt tolerant pins, so it doesn't matter if I use 5-volt to power up the ultrasonic sensor. You can follow this circuit diagram. Before we start the programming, first we will need to connect the STM32 board to the laptop or PC. For this, we are going to use the ST-Link V2. Simply connect the ST-Link V2 3.3 volt and ground pins to the 3.3 volt and ground pins on the STM32 board. Connect the SWCLK and SWDIO pins of the ST-Link to the STM32 SWCLK and SWDIO pins. Finally, connect the ST-Link V2 to your laptop or PC. I'm going to continue with the same OLED display module programming. Go to the OLED.ioc. I'm going to use the same SCL and SDA pins for the OLED display module. Go to the system core and click on the RCC. Select crystal or ceramic resonator. Next, go to timers. Select timer 1. Select the clock source as internal clock. Next, click on the PA8 pin and select timer 1, channel 1. Next, go to the connectivity, and as you can see, I'm using the same I2C for the OLED display module. Next, click on the PB9 and set it as output. Then click on the PB8 and set it as input. Then go to clock configuration and change the HCLK to 72 MHz. Finally, click on the save button. If it asks you, do you want to generate code? Click yes. Again, press the yes button. STM32 CubeIDE will generate the necessary code based on your pin configuration and open the associated perspective. This perspective provides you with the appropriate tools and views for further development and customization of your project. I've already written this code for you, so simply copy and paste it in the main.c file. More than 70% of the code is automatically generated. I only added this portion of the code in the while function. And I also added these pins definitions and defined some variables. Anyway, once your program is completed, then you can save the program. And click on the hammer icon to check for any errors, and finally click on the play button to run the project. We just built ourselves a distance measurement system using the HC-SR04 ultrasonic sensor, an OLED display module, and the STM32 microcontroller board. So that's all for now. Support me on Patreon for more videos. I hope you liked today's episode. Like and share this video with your friends. See you in next episode, and thanks for watching.